The following is a presentation to the AAI, or Amateur Astronomers Incorporated Club of New Jersey, on December 16th, 2016. A hard copy of this presentation can be found on my website at astrodentist.com, and I can be contacted directly via email at dennis@astrodentist.com. What you see in the upper right corner is the sort of more traditional way that exoplanets are detected. And I know that some of you there in the audience have actually done exoplanet observations. And that method is the so-called transit method, where as a planet goes in front of its host star, there's a dip in the light of the host star. And based upon the characteristics of the light curve that results from that, in particular the length of the dip and the depth of the dip, there are certain characteristics of the planet and its orbit that can be gleaned from that light curve. And that is the most common technique used by amateur astronomers, and it's also the most popular technique that has been used so far to detect over 3,300 exoplanets. And principally that was through the Kepler Space Telescope mission. So the transit method has been the dominant method, but there's another method that I think is quite interesting, and that's using something called microlensing, and that's what will be our topic this evening. So by way of background, Einstein, in his general theory of relativity, predicted that an object that has mass can warp space-time around it. And the implications of that is that light passing near that object, near that mass, will get diverted and will create one or more additional images. So in effect, any mass can act as sort of a lens where light that is coming near that mass can actually get warped around it. Now, microlensing is a particular gravitational lensing approach that uses a background star, we call a source star, that gets lensed by a foreground object. And we'll see some examples of this in a minute. So microlensing is a particular case of gravitational lensing, which is based on Einstein's theory of relativity. Now, microlensing, because what we're talking about here is a foreground object, that is to say, an object between us and a distant star, where that object between us and that distant star moves between us, the most high probability way for that happening is for us to be looking toward the center of the Milky Way. Now, why is that true? Well, because that's where the density of stars are, and the higher probability of a planetary system or a star system moving between us and another star system. So the observations for microlensing, unlike the transit method, are principally concerned with observations toward the center of our Milky Way galaxy. And as a foreground star system moves in front of a background star, the light of that background star, that is to say of the source star, will change. The light curve generated by that movement of the foreground object will cause an extreme change in the light curve of the source star. So imagine a star sort of in the middle of the Milky Way galaxy, and halfway between us and it is another star system that moves between us. All of a sudden, the light of that background star is going to increase. And that's the whole principle of microlensing. And we're going to go into more detail about this in a second. By the way, when I say throughout this presentation that a foreground object moves in front of a background star, strictly speaking, I really mean the combined relative motion of a foreground object and a background star relative to an observer here on Earth. In addition to being able to detect exoplanets, in particular, what's nice about microlensing is it can detect Earth-sized planets. Unlike the transit system, where we're looking at the drop in the light of a star based on a planet moving in front of it, typically that transit method is used to detect what we call hot Jupiters, namely large planets of the size or larger than Jupiter. Earth-sized planets would hardly be detectable using the transit method, but with the microlensing approach, the advantage of it over the transit method is the ability to detect Earth-sized planets. And finally, us amateur astronomers have been able to help the professional astronomers conduct microlensing observations. And in fact, we're going to be talking about one that I conducted just a few days ago. Mary Lou alluded to it in her research report, and we'll see an actual example of an amateur astronomer observation of a microlensing event. Okay, so one of the things you may have already seen in various magazines and such is the gravitational lensing of a galaxy by another galaxy. And in fact, what you see here is a foreground galaxy lensing a background galaxy. And it just so happens that if the geometry is just right, that background galaxy forms a ring around the foreground galaxy. And that ring is of a certain diameter. And in fact, if it's perfectly aligned, it will produce a ring, as you see in this picture. And that ring and the diameter of that ring is a so-called Einstein ring. And that is sort of one of the keys to microlensing, as we'll see in a second. So on a cosmological scale, that is to say, when we're talking about galaxies, microlensing other galaxies, we certainly have already seen some examples of that that Hubble has produced, as you see in this picture. Now, microlensing is more on a local scale. That is to say, we're looking at, as you see in this picture here, if our solar system is this sort of orangey sort of blob here, what we're looking at is looking into the center of the Milky Way galaxy, and we're looking at star systems that lens source stars that are closer to the center of the Milky Way. So these microlensing events that we see here in various arms of the Milky Way galaxy are lenses effectively of background stars. But it's these systems here that in fact are the ones that have either binary stars or exoplanets orbiting them. So unlike on a cosmological scale where galaxies are lensing galaxies, what we're talking about here are stars that are lensing other stars. And again, we're mostly looking towards the center of the Milky Way. Kepler, which has used the transit method, has mostly detected exoplanets in our arm, for example, of the Milky Way galaxy. Now, in looking at the center of the Milky Way, as many of you observers who've ever tried to either image or looked into the Milky Way, it's a very crowded field. Well, it turns out that there's a window called Bod's window, which is not quite as dense as the other areas around the center of the Milky Way. And that has become sort of the primary area where microlensing has taken place, because there's not that much dust that obscures some of the source stars in the middle of the Milky Way. So the Bode window is a particular area very close to the galactic center that microlensing observations focus on. So let's review again what microlensing is. If we have a source star, let's say that's close to the center of the Milky Way and an observer here on Earth, and all of a sudden, if a planetary system, let's say that has a star and a planet, moves between us, the observer, and the source star, a microlensing event takes place. Now, this intervening system could be, as shown here, a star and a planet, or it could be two binary stars, or it could be a triple star system. But it's any system with mass that, again, according to Einstein's general theory of relativity, will cause warping of space-time and will cause the light of that source star to bend. And from our point of view, we see a brightening. And we'll see in a minute why we see a brightening and not multiple images. Okay, so that's sort of the basic framework of microlensing. And one of the things that we will see is that theoretically what is happening is there are multiple images actually being produced, but because of the resolution limitations of us as observers, we are not able to resolve those multiple images. And so what we see is one bright star, namely the source star, get even magnified greater, when in fact what's happening is what's really happening is multiple images are occurring. But from our point of view, it looks like it's a brightening of the source star. But if we were to have milli-arc-second sort of resolution, one would actually be able to see multiple images. But we just don't have that capability to make that fine resolution. So I mentioned earlier the Einstein ring. What the Einstein ring is if I have a mass with mass size of m, and let's say in this example, let's suppose we have a single point. That is to say, we have a single star. We don't have a planet and a star. We don't have multiple stars. So for simplicity, let's just say we have a single point. There is a well-defined radius that will affect light coming anywhere near or through this ring being called the Einstein radius. And we'll see in a minute the formula for that ring or for that radius. And in fact, if I say that the distance from the observer to that intermediate lens or to that mass is dl, and the distance from the lens to the background star is dls, and the distance from us, the observer, to the source star is ds, the formula for the size of that ring is what you see here. 4 times the gravitational constant times the mass of the star in the middle over the square of the speed of light times the distance from the lens to the source over the distance from the observer to the lens and the distance ds from the observer to the star, square root. So there's a well-defined formula for computing how big the lens is around a given mass relative to an observer at a certain distance and relative to a source star in the background. All right, let me stop there, and Aaron, maybe let's just see if anyone has any questions. You can either maybe repeat the question or have that person ask the question themselves.
What's the reason why we don't have that sort of resolution yet to be able to image the multiple images?
Okay, the reason we don't have that resolution is because if you do the computations, let's say we're looking at, for example, into the middle of the Milky Way galaxy, and let's suppose the lens is halfway between us and the Milky Way. And that, by the way, that scenario is one that astronomers often use to sort of give us an example. For us to be able to resolve those images that are created, and we'll see on the next slide that as an example, one has to have milli-arc-second resolution. And as you may know, the best observatories on Earth, for example, maybe half an arc-second resolution. Us amateur astronomers, 2 to 3 arc-second resolution. So we're talking milli-arc-second resolution. A millionth of an arc-second is what would be needed to resolve those images, which is just not within the realm of our current instrumentation, or whether it will ever be, especially certainly here on Earth, given the effects of seeing conditions and so on. Okay.
Oh, hang on, we got a couple more.
Yeah, sure.
The question is, you'd also see an Einstein ring if the lensing object was a black hole as opposed to a planetary star system.
Correct. Well, anything with mass. So a black hole would have mass, and that certainly would seems to me act as a lens. And in fact, I think Aaron, the paper that you had referenced, I think suggests that, if I'm not mistaken.
We have a question about the theoretical resolution for imaging from space, from say Hubble.
Yeah, Hubble is still not going to get milli-arc-second resolution. I can't tell you offhand what the resolution is, but we're still not there even with our current space telescopes. Now, what is possible, I will say, is that, and what has occurred is the ability for two different space telescopes where they're on two different parts of Earth's orbit. They're able to do a parallax measurement and be able to determine the distance to the lens. Right now, just a single observation of a microlensing event, you can't tell the distance to the lens, but a parallax measurement with two different space telescopes has been able to at least resolve the distance, not resolve the images. Any other questions, Aaron?
The question is, if there are two objects lensing in the same line of sight at the same time, how would that change your observations?
Okay, we're gonna actually get to that in a minute. So if we could hold off on in fact, that is a key part of detection of exoplanets.
All right, I think that's all the questions for now, Dennis.
Okay, good. All right, so let's take a look at this formula in a slightly different way. And let's look at what affects the size of the Einstein ring. So just based on the formula itself, you can see that the radius of the Einstein ring is going to increase if the mass increases. So the larger the lens, larger the mass of the lens, the bigger the radius. The greater the distance between the lens and the source star will cause the ring to increase. And again, what we're talking about is between the lens and the source star. So the greater this distance, the bigger the ring. Or if the distance between the observer and the lens or the source star decreases because it's in the denominator, then the ring is going to increase. So if the distance between the observer and the lens, for example, is smaller, the ring will be bigger. So there's a number of variables that affect how large the Einstein ring is. Okay, so let's take a look, a little bit more detail here. So here we have, again, the observer, we have our source star, and we have a lens in the middle, some mass, and its Einstein ring. And let's suppose that in this example, the source star is not quite directly in line between us and the lens. So let's say it's offset a little bit, which is, generally the more typical case. So in that case, what's going to happen is the light from that source star is going to hit the ring, get diverted, and we're going to see, although it's not resolvable, there will be a second image of the source star, and we'll see that image as if it's up here. Now, again, we're not going to see it, but the light from that sort of pseudo image, if you will, is going to represent itself by a brightening of the source star. Likewise, there will be another image that will be formed on the other side of the ring, again, based on the light rays from the source star being bent a little bit closer to the lens. So the three images, the original image of the source star and the other two images, all sort of merge together into one bright object. And from our point of view, it's as if this source star brightened all of a sudden as it moved across the Einstein ring. So imagine the source star is, let's say, moving in this direction, is moving up. And what you're going to see happening is that its brightness from the observer point of view is going to change because the corresponding sort of virtual images are also going to be changing. And ultimately, as the source star moves outside of the Einstein ring, it's going to be back to its normal magnitude. So if the source star starts here and we're looking at it, and it's, let's say, magnitude 18, and it starts proceeding, it hits, its light rays hits the Einstein ring, they get magnified, all of a sudden its magnitude might go to 17, then maybe it might go to 16, and then might go back then ultimately back to 18. So as the source star moves in its direction with a certain velocity, its light rays are going to get magnified from the point of view of the observer. Okay, now let's add a little mathematics to this geometry here. If the angle between the direct line from the observer to the lens, the angle from that to our observation of the source star is theta s, if we then say, if we then take a look at the angle between the, again, our line from the observer to the lens and this other image is the plus version of that, and here is the minus version of it. The combined angle, or each of those angles, I should say, is given by this formula. Now, I'm not expecting you to, know this formula, remember it. The point is that the if the angle here is 0, namely if the source star is directly in back of the lens, and you just plug 0 into the numbers here, what you get is that this theta value is in fact the size of the Einstein ring. So it all works out. So again, the math is just to show you that there are relationships between the angles of the source star and the observer, as well as these virtual images. So let's take an example. If let's say the lens has a mass the size of our sun, and let's suppose that the distance to the galactic center from the observer, from us on Earth, is 8,000 parsecs, or 26,000 light years, which is the distance from us to the middle of the Milky Way galaxy. And let's suppose that this lens is halfway to that distance. If we compute the size of that Einstein ring, you get 1 milliarcsecond, as I said earlier, which is too small for our telescopes to resolve. So in fact, you can plug formulas, you can plug numbers into the distances and the mass, and you can figure out how big that Einstein ring is. And where this is important, as we'll see later, is it helps astronomers figure out certain characteristics if it happens to be that that lens is a star and a planet. And we'll see that in a moment. So let's take now a couple of examples of a star going across, a background star going across the Einstein ring at different segments of the ring. Well, if the star passes the ring altogether, then it's not going to show any kind of increase in magnification. The closer that background star gets to the middle of the lens, the sharper the increase, the sharper the increase in light. In fact, if that background star passes very close to the center of the lens, there is a very large magnification of the light curve of that background star. And in fact, it's this all of a sudden increasing in magnification that clues astronomers to the fact that a microlensing event is taking place. So what these microlensing surveys do is they're just looking at the magnitude of stars, and all of a sudden, if they see the magnitude of a star start increasing by a certain threshold, then they would put out an alert saying, I think we may have a microlensing event. And in fact, as that curve starts increasing and it reaches a peak, then the characteristic curve, if it's just a single lens star in the middle, will show this sort of characteristic curve. And based upon the amplitude of that curve, there are certain characteristics about the mass of that lens that astronomers can determine. So the principle here again is that the closer a star transits to the middle of the Einstein ring, namely to that mass, the sharper the curve is going to occur. Now, what happens if there's a second mass in the Einstein ring? So what we've talked about up to this point is there's a single mass, a single star. What if there's another star? Or what if there's a planet orbiting that star? It's going to change the characteristic light curve in certain ways. And let's see what happens. Well, if there is a second mass, that could be a star, such as a double star or a planet. What happens in both cases is there's something called a caustic region that's formed within the Einstein radius. And that caustic region is bounded by what's called a critical curve. Now, what's a caustic region? Well, in everyday life, we would see a caustic region and a caustic curve if you just take a cup, round cup, and doesn't even have to have any water in it, if you just reflect light into it, what you're going to see in the bottom of the cup is a caustic region. I don't know if you can see it plainly on your screen there, but there's this area at the bottom of the cup that represents parallel light rays that have hit the circular part of the cup and have converged to form this caustic region. And that caustic region, if you were to look carefully, you would see very sharp curve around the caustic region, that being called the critical curve. In very much the same way, it doesn't have to do with light, it more has to do with gravity, that if there's a secondary object, what is formed is a caustic region in the Einstein ring. And we're gonna see that in a second. And that caustic region in the Einstein ring also has a critical curve in it. And we're going to see how when a background star crosses through the Einstein ring, and if it happens to cross through that caustic region, there's going to be other perturbations to that light curve. All right, so let me stop here, and Aaron, maybe you can see if there's any questions.
How can they tell the difference between a microlensing event and a variable star?
A variable star is going to periodically occur, for one thing, and a microlensing event is a one-time deal. So that's one way. The other way is that the variable star, I would imagine, is going to have a different light curve shape. And variable star is more likely to dim and then brighten, as opposed to constantly stay, as opposed to a microlensing event that's gonna brighten. So so I would say in those two ways.
Question is when you're doing the data collection, how do you subtract out the light from the source star in the background? Or the light from the lensing star in the middle?
Well, the lensing star in the middle actually is so faint that it's not even gonna, you can't even see the lensing star in the middle typically. I mean, if it, once the source star passes in back of it, typically these are, you know, brown dwarfs or are masses that don't even have enough light to detect in most cases, except for, you know, like galaxies and that sort of thing.
One more question.
I'm sorry, did you say no more?
One more. The question is, why did they pick the word caustic to describe these regions?
Yeah, caustic is Greek for burn. So it's basically concentration of light in the case of the cup example, or concentration of gravitational effects in the case of microlensing. So caustic is derived from, you know, just like caustic soda, if you're familiar with that term from way back. So yeah, it's more the Greek derivation of burn.
That's all the questions for right now.
I'm sorry, did you say that's all?
Yeah, that's all the questions for right now.
Okay, all right. Okay, so so again, here we have a caustic region and the caustic critical curve in this little example of a light. By the way, just for you telescope folks, you've heard the term spherical aberration. What you're seeing here in this cup example is spherical aberration. Namely, it's a parallel light rays hitting a curved circle produce this interference pattern, not this interference pattern, but this pattern in the middle. If this were a parabola and parallel light rays were hitting it, it would converge to a focus point. So we talk about spherical aberration in the case of telescope lenses to sort of indicate the extent to which our telescope isn't producing, isn't creating a true focus point with parallel light rays, but in fact is creating sort of, again, a kind of a caustic, because there is a certain circular part to our, what we thought is a parabolic surface. That's just a kind of aside. Okay, so here's some examples of microlensing caustics. Two double stars that have created an Einstein ring create this weird kind of caustic, and a background star that happens to cross that Einstein ring, if it hits one of these caustic regions, its light curve is going to have a characteristic blip to it that we're going to see in a second. And depending upon how it crosses the caustic, what angle it crosses, which part of the caustic, its light curve is going to change differently. We're going to see an example. Another caustic, is another example is here. If the two binary stars are closer together, then the caustic regions are as you see here. So depending upon the distance that two masses have from each other, and depending upon the relative mass of each other, different caustics will be produced. Now, and we're going to talk about that later in a minute, but let's take an example of a caustic. This particular caustic is produced by two binary stars, and if this yellow thing is the background star, and let's say it's crossing the caustic in the manner you see it, what its light curve is going to look like is this. It's going to be approaching the caustic. When it hits this critical curve, there's going to be a spike in amplitude. As it's going through the caustic, that amplitude is going to be reduced, not quite down to its nominal size. When it hits again the critical curve on the other side, there's going to be another spike and then down again. So by looking at the light curve, when these caustic crossings occur, astronomers are actually able to discern what the caustic look like, and from that they can discern what caused the caustic, namely if it's two binary stars or if it's a planet and a star. So the shape of the light curve is directly related to the type of caustic and where the background star crossed that caustic. So this little table here, it shows the relationship between, as I said, the distance between two masses that are in the Einstein ring and their ratios. So the example we saw earlier is on the upper left, two binary stars that are close together that have a ratio of 1, namely the same mass, produce this particular caustic pattern. Whereas if they're further apart, but still of the same mass ratio, they'll produce a different pattern. And if the mass ratios are way different from each other, as would be the case with an exoplanet and a star, then it would produce these sorts of caustics on the bottom of the chart here. So again, based upon the type of caustic, one can determine the distance between the two masses and their ratio. So these are sort of well-defined caustic patterns that occur because of that. So let's suppose we do have a planet that creates a caustic. So we've got a planet orbiting a star that is in the middle of the Einstein ring. In this example, this little caustic here is what was created by that planet. And if our background star happened to cross the caustic of that planet, what one would see is not just the normal light curve if it was just a single star, but would be this little sort of blip that would occur. Now, the time to cross this caustic caused by the planet is in the order of hours. And what's important about that is that as astronomers see that a microlensing event is starting to occur, it's important that there be very frequent observations of it in order to catch the case on the order of hours that it might be a planetary caustic. And this again is one of the reasons for amateur astronomers being involved in these microlensing follow-up observations, is because we have the ability to do a lot of observations from different points on Earth. So detecting planetary caustic crossings are very transitory, again, on the order of hours, and it requires observations happening quite frequently. If it were a double star that was causing a caustic, then we're talking about those being on the order of days, as we saw on this chart here. And the time to completely cross the Einstein ring could be on the order of weeks. So the complete crossing, this overall curve here, is on the order of weeks. So you can see that there's different time frames based upon the different caustics and how long it takes to go across the Einstein ring itself. So what can we learn from the light curve of a planetary caustic crossing, namely of a star that is a background star that happens to be cutting through a planetary caustic? What we can tell is, again, the ratio of the mass of the planet to the primary star, and we can constrain the distance from the planet to the star. So basically, on this diagram here, we can sort of indicate, where in this diagram we are. Now, again, it's all relative. So we're not saying we're getting the mass of the planet. We're getting the ratio of the mass of the planet to the mass of the primary star. So what good does that do us as far as coming up with the mass of the planet? Well, there are, in some cases, assumptions that astronomers make as to the mass of the lens star. I've seen in the literature, in some cases, they assume it's, on the order of our sun, in which case, you do get sort of some estimate of the mass of the planet. So, there is some, some assumptions that go into what these calculations, how these calculations help us to determine characteristics of the planet and the star itself. Okay, so let me just stop there, and Aaron, maybe see if there's any questions before we get into an actual microlensing observation.
Question was, what sort of historical catalog is kept on the Einstein rings and the paths of the source stars?
There's actually quite an extensive collection of microlensing events, and there's at least 2 different organizations that are cataloging previous microlensing events as well as candidates, and I'll give you those references actually at the end of the presentation. I do have those. So there are catalogs of previous microlensing events that have taken place. Any other questions?
Tonk is asking what the confirmation process is for the discovery of these planets.
Well, there's two events that will take place. In fact, I think if we go to the example, I think that will actually show how those conformations occur. So let me hold off on that question and just see if there's another question.
That's all the questions for now, Dennis.
Okay, all right. So let's take that question, and in fact, let's use a particular example. There was a notice that went out recently. Gaia is, as some of you know, the survey that has just been completed. In fact, it's sort of the latest and greatest survey of millions of stars. And one of the things that Gaia is doing also is seeing if there's any change in the magnitude of stars, which might indicate the beginning of a microlensing event. And what happened is an event occurred rather recently that was deemed to be the crossing of this caustic that you see in this picture of a background star. So this line here is the trajectory path in the background of a source star crossing the plane of the lens, and in particular crossing the caustic. And you can see it hits the critical curve here, kind of comes out a little bit, goes back into the caustic, crosses the curve again, and then out of the Einstein ring. Now again, what you would expect is that when it hits this critical curve, there's going to be an increase in magnitude. So there's going to be a magnification. Then when it goes into the caustic, it's going to be somewhat magnified, but again, it's going to hit another part of the critical curve. There's going to be an amplification. It's going to go out of the caustic. It's going to come back in. So you're going to see different spikes here as you go through this caustic. In fact, this caustic in this path was derived from the light curve that you see here. So what astronomers, to answer the question in terms of confirmation, at a certain point, and I forget, there's a sort of built-in trigger that says once the magnitude hits a certain level, then alarms and bells go off indicating this might be a microlensing event that's happening. And what you see here are observations. These little dots are different observations that were made, land-based observations that tracked this light curve. And each of these little spikes is when that source star crossed the critical curve of the caustic. And as I said, you see it crossed it, it came into the caustic, crossed it again, went out of the caustic, crossed it again, stayed in the caustic, and then all of a sudden completely exited the caustic and started declining back to its normal magnitude as it exited the Einstein ring. So to answer the question about confirmation, it's basically taking observations of the light curve that will show a characteristic pattern that astronomers then derive what that caustic looked like and what the path was that the object took. This observation was done just in the last, well, I should say that this last crossing occurred just in the last couple weeks. And in fact, a notice went out just a couple weeks ago to have amateur astronomers take observations of this particular source star to determine what the magnitude was. And I was fortunate enough to have a clear night that night and was able to get, in fact, an observation right at this point on the last crossing of the caustic. And so if we sort of magnify that last crossing, it sort of looked like this. Some of these blue and green ones were from professional observatories, and I was one of 2 observers that were able to catch it on the downward slope here. And in fact, I caught it right at this point And in the course of, this was not that long, maybe an hour or two, you can see this extreme drop in magnitude because we're coming down this steep slope here. So this was an extreme drop in magnitude, relatively speaking, from 1.02 to 0.94, it looks like. So about an 8% drop in magnitude, which is just huge over the course of an hour because we're on this fast downward slope. So this particular observation I made is very important to the professional astronomers because it helps them to constrain where this downward slope is occurring, which helps to constrain what that last caustic region looked like. So bottom line here is, you know, amateur astronomers like myself with a little old 11-inch backyard telescope in light polluted Annapolis can do some good science in the case of helping with some of these microlensing events. Like I said, I was only one of 2 observers who were able to catch it on this downward slope. And in fact, my observation was tweeted out to the international community, and my images are currently being processed for the professional astronomers as far as who are involved in that particular microlensing event. So that microlensing event was of a double star, not of a planetary system, but the same sort of process would apply. An alert would go out that a microlensing event is taking place. Amateur astronomers would turn their telescopes to that target, collect light curve information, and hopefully help the professional astronomers discern what kind of caustic was occurring and therefore what kind of associated mass with the primary lens, and whether it was then a double star or whether it was a planetary system. And in fact, these are 2 images I took November 21st. If hopefully you can maybe see on your screen, but you can clearly see it if you bring up the PowerPoint itself. This is the target star, and you can visually see the drop in magnitude just visually looking at it in the course of one day. How it went from, you know, that sort of brightness down to that sort of dim sort of star. So just to kind of summarize here, how can amateur astronomers participate? Well, one of the advantages is we can act on short notice. As we just saw in this example, we've got worldwide coverage where we're not constrained. You know, we've got amateur astronomers around the world, different time zones, different geographic coverage, you know, northern, southern hemisphere. We can do simultaneous observations, so we can reduce uncertainties. We can work around weather issues. I know Jim, I think, was trying to do this observation up in New Jersey. He got clouded out. Fortunately, I had clear skies down here. To get to the question that was asked earlier about surveys and catalogs of this information, OGO is one of the biggest projects for microlensing, and in fact, they provide microlensing alerts. They also have a catalog of microlensing events that took place. Ohio State has had this project called Microfund, Microlensing Follow-Up, where amateur astronomers were contributing to microlensing observations. It's now supporting a Spitzer microlensing program through 2018. I've been in touch with the principal investigator, and she has said that anybody that's interested can email at this email address. Again, this is on my website. You can go and take a look if you're interested in getting alerts. You can also go to the OGLE, just Google OGLE and you get to their website. You can sign up for any OGLE alerts that also are occurring. So to summarize, it's clear that hopefully you've been convinced that astronomers, professional astronomers, can determine certain characteristics just based upon the light curve and based upon therefore the kind of caustic that is formed. And amateur astronomers were ideally suited to help the professionals with follow-up of microlensing events. So let me, Aaron, see if there's any questions. That sort of concludes what I had prepared, but let's see if there's any questions.
Oh, yeah. Glenn? Glenn's asking, which definition of magnitude are you using? Because some of the graphs showed magnitude going up when it was brighter, but that's not the magnitude we're familiar with.
No. When I'm sorry. Let me back up. Yeah, I should be. If you look at this chart here, for example, as you know, magnitude here. Let me see if I can see what the actual numbers are here. If we're going from 14 to 12, for example, as you know, magnitude when it's lower actually means brighter. So I don't know if that answers the question, but this indeed is magnitude. I don't know if the question was what filter, if it's V magnitude or whatever, but the point is this chart is in magnitudes, not flux and not amplitude. So it's, as something gets brighter, the magnitude gets smaller, as it should. Does that answer the question?
Yeah, that takes care of it, Dennis.
Okay.
Mary Lou, do you have a question? The question for Mary Lou is, how many planets have been discovered with this method?
There have been, let's just go back to one of the charts here. Ugol has, I think, about a dozen. Yep, there we go. The Ugol has, I don't know, what is that, maybe a dozen or so. There's I think the last I think I saw was there have been, well, it's a small number, let me just say that. And one can go to NASA's website and pull up what that number is, but it's, it's not great, not a large number.
Dale?
I'm sorry?
A question from Dale Gary. Question from Dale Gary was, one of the paths of the star through the caustic region was curved. He was expecting it more to be of a linear fashion.
You're talking about, I think I know what you're talking about. Let me bring it up. It's probably the example. That one there, is that the one he's talking about?
Yep, that one.
Yeah. Yeah, that occurred to me too. I think what that is that there's relative motion occurring probably on three different levels. The lens itself, that star is moving, the background star is moving, and we're moving. And so relative to each other, I think we're just seeing this sort of curve shape, it appears as if it's a curve. I mean, the star itself, the background star is moving in a linear fashion, but the effect is as if there's a curve, I think.
The question was about any possible concerns for repeatability, because these are one-time events. Is there any concern that there may be any errors in the data because it's not repeatable?
Yeah, well, I think the answer is that's why a number of simultaneous observations are important. And certainly, my observation has larger error bounds than a professional observatory. So I think the answer is, the more simultaneous observations, the better able to constrain the errors. But it is a one-time event, and it's there or it's not. So, yeah.
Question was, we have the names and identified which stars these are in catalogs, that we know which stars are the ones that have the planets, and we know where they're cataloged?
Are we talking about microlensing events that have already occurred where planets have been identified with them? Is that what we're talking about?
Yes, yes, current already happened events. The question is regards to the fact that you had stated that often the lensing star is too faint to see in comparison to the Einstein ring.
Right.
So are these stars that are in known catalogs, and do we have a list of them?
We're talking about the source stars or the lens stars? The source stars?
Lensing stars.
I don't believe so. I think the only thing that we know of in a catalog is the source star itself, because as I said, I'm not aware that the faint object moving in front of it is even in any catalog because it is so faint. So I'm not, I think the answer is no, just the source star.
All right, that's all the questions, Dennis. Thank you very much. We look forward to seeing you back up in New Jersey soon.
Yep. Okay. Look forward to seeing all my AAI friends. All right. Thank you all.